Typically, cells use AMPK as a sensor for when they are low on energy. This happens when there's not enough glucose or nutrients, and they activate AMPK as an emergency lighting system to say, we don't have enough energy, we need to stop and shut off everything using energy, and we need to get more nutrients into the cell, pronto.
We started really heavily with genetic crosses so that we could very cleanly inactivate AMPK within the primary tumor cells at the moment that the tumors were turned on, basically. And so then we could study what happens over time as tumors develop, either with or without AMPK. We found that the tumors grew much slower when AMPK was not present.
Very small tumors don't require AMPK because they have enough nutrients and they can sustain their own growth. However, once they get past a particular size, they are now too many cell layers away from the bloodstream to appropriately obtain oxygen and glucose to sustain their continued growth. Under those conditions, that's where you see activation of AMPK. But the big surprise in this study was that AMPK also sends a signal that helps cells recycle their own components, that allows the cell to cannibalize its own nutrients more to stay alive during the times when it can't get nutrients from the outside. And that is a very specific advantage. I'm particularly excited about the therapeutic implications of the work because most people come to the clinic and it turns out they have a tumor and they've had the tumor for a while and they simply didn't know it. In those advanced, hard-to-treat solid tumors, this is where this new information will help us try new therapeutic possibilities.
LKB1 mutant tumors, there are no, aside from chemotherapies which don't work that well, there's no treatments for that entire class of patients with those mutations. So any concrete step, solidifying a set of knowledge is extremely helpful.